Assalamualaikum, students and friends. Welcome to today's episode, which concerns the physics of a moving yo-yo. We shall look at how the law of conservation of mechanical energy can help us in analyzing rotational motion. So hang on, stick around, watch and learn. Here is the question. A primitive yo-yo has a massless string wrapped around a solid cylinder with mass of 200 point grams and radius of 2.00 centimeters. You hold the free end of the string stationary and release the cylinder from rest. The string unwinds but does not slip or stretch as the cylinder descends and rotates. Using energy considerations, find the speed v sub cm of the cylinder's center of mass after it has descended a distance h equals 1.00 meter. And here are the given quantities. We have the mass of the yo-yo, small letter m, equal to 200 point grams. That means in three significant figures. We have the radius of the yo-yo, denoted by small letter r, equal to 2.0 centimeters. This is the radius of the cross-sectional area of the yo-yo, which is cylindrical in shape. We're also given the distance traveled by the yo-yo, denoted by small letter h, 1.00 meter. And initially, the speed of the yo-yo, more specifically, the speed of its center of mass, is equal to 0 when it's still at point A, as seen in the figure. And our target variable is the speed of the center of mass of the yo-yo after it has descended a distance h, or when it is exactly at point B. It is required in the problem that we have to use or apply the law of conservation of mechanical energy in analyzing the motion of the yo-yo. So we say that at point A, all right, the gravitational potential energy of the yo-yo, denoted by capital U's of naught or U naught, is expressed as mgh, or the product of the mass, acceleration due to gravity, and the height h. And its initial kinetic energy, k naught, of course, is equal to 0 because the yo-yo starts from rest. And then, at point B, when the yo-yo has reached, all right, point B, which incidentally is also our chosen reference, we say that its gravitational potential energy, capital U sub 2, will be equal to 0, right? and that the kinetic energy final, K2, will just be equal to the sum of the translational kinetic energy of the yo-yo and what we call the rotational kinetic energy. So K2 is equal to 1 half the mass times the square of the speed of the center of mass of the yo-yo. Alright? We call that the translational kinetic energy at point B. Alright? While 1 half times I sub Cm multiplied by the square of omega, alright, represents the final rotational or angular kinetic energy. Alright? So the law of conservation of mechanical energy can simply be written mathematically in this manner. Alright? Capital U naught, which is the initial gravitational potential energy, that is at point A, plus the initial kinetic energy, K naught, alright, is just equal to the gravitational potential energy, capital U, sub 2, that is at point B, plus the total kinetic energy, K sub 2, also at point B. So, capital U sub naught or U naught is expressed as mgh. Alright? It has no K naught. That is understood to be 0. So, this will be equated to the sum. Alright? The sum of the translational kinetic energy and the angular or rotational kinetic energy. 1 half mass times the square of the speed of the center of mass of the yo-yo plus 1 half times the product of the moment of inertia of the yo-yo and the angular or the square of its angular speed. Alright? Omega squared. Alright. Recall that in rotational kinematics, we have this expression that relates the angular speed omega to the translational speed b sub cm. Alright? That is, omega is just equal to b sub cm over the radius r. And we also have the formula for the moment of inertia of any regular solid cylinder. Alright? The yo-yo, incidentally, is or has a shape of a solid cylinder. So its moment of inertia about its center of mass is just equal to 1 half times the mass and the square of the radius. Alright? The radius of the cross-sectional area of the cylinder. Alright? Moving on with our derivation. Alright? So we said that based on the principle of conservation of mechanical energy, alright, the total mechanical energy of the yo-yo initially, when it's at point A, is just equal to the gravitational potential energy, denoted by capital U naught. There is no kinetic energy because it started from rest. Alright? And all this total mechanical energy will be converted to kinetic energy when the yo-yo reaches point B. Alright? The total kinetic energy of the yo-yo is denoted here by capital case of 2, meaning the final kinetic energy, or that is expressed as capital U naught is actually mgh, while case of 2, or the total kinetic energy of the yo-yo, is just the sum of its translational kinetic energy 1/2 mv squared, where the v is the speed of the center of mass of the yo-yo, plus its rotational kinetic energy expressed as 1/2 times the moment of inertia of the yo-yo, which is a solid uh, cylinder, okay, times the square of its angular speed, omega. All right. So uh, what we want is to substitute the moment of inertia, capital I, in terms of mass and the radius r. And earlier we said that the angular speed, omega, is just related to the transitional speed, b sub cm. All right. That is, omega is equal to b sub cm divided by the radius r. Likewise, the moment of inertia of a solid cylinder, I of cm, is just equal to 1/2 times the mass and the square of its radius. All right. So K2 can now be simplified further as, all right, 1/2 mass times the square of b sub cm plus 1/2 quantity, all right, 1/2 mass times the square of r, all right. That is initially the moment of inertia of the yo-yo of a solid cylinder, all right, while omega has been replaced by b sub cm over r, but still has to be squared. Okay, so we can further simplify this into K2 is just equal to 3/4 of the product of the mass and the square of the center of, or the speed of the center of mass of the yo-yo. And since our target variable is b sub cm, all right, we can isolate b sub cm, but we have to equate this to u naught, or capital U naught, or mgh. All right. So mgh is just equal to 3/4 the mass times the square of b sub cm. And isolating b sub cm, we now come up with the working formula for b sub cm. And that is just equal to the square root of 4/3 multiplied by gh. All right. So this equation implies that the final speed of the yo-yo as it descends from the height h and reaches point B, all right, its final speed, specifically the speed of its center of mass, will not be equal to square root of 2gh. If you recall, square root of 2gh is the final speed of any freely falling body starting from rest and falling through a height h. All right? So in a short while, we will continue with our calculation for V sub cm. Finally, we now calculate for the speed of the center of mass of the yo-yo, which is equal to square root of 4/3 multiplied by g and the height h. That is square root of 4/3 times 9.80 meter per second squared times 1.00 meter. So doing our math, we will get the speed of the center of mass of the yo-yo equal to 3.61 meters per second. Alright? Now, if the yo-yo was moving like a freely falling body and was not rotating, the final speed of its center of mass would be equal to square root of 2gh. Alright? If you recall, this is the formula for getting the final speed of a freely falling body that starts from rest, alright, in falling from a height h. Alright? So, if the yo-yo is like a freely falling body, right, its final speed or the speed of its center of mass would have been equal to 4.43 meters per second. Alright? Um, it is, of course, greater, alright, greater than what we get here in this problem situation. Alright? We say that uh, the speed of a body, alright, when it is rotating at the same time translating, it's going to have a less uh, speed as compared to when it's just translating. Alright? The reason is that in the situation, part of the total mechanical energy of the yo-yo has been converted to rotational kinetic energy. Alright? In moving from point A to point B. So, what happens is that the translational kinetic energy, okay, has been decreased. And that explains why the translational speed of the yo-yo or the center of mass of the yo-yo is also less, okay, than what it would have been if it were not rotating or simply falling like a freely falling body. All right? So, before we end, let's just emphasize the concept that we applied in this problem situation. We say that if a rigid body is both translating and rotating, its total kinetic energy would just be equal to the sum of its translational kinetic energy and its rotational kinetic energy. So that's it. We are done. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.